Good evening, students. I hope that you can hear my voice. And we will continue our discussion on mass spectrometry. And we are discussing the fragmentation pattern of a couple of organic compounds. And many organic compounds we have discussed, like we started with the alkanes, hydrocarbons, and then the alkenes, alkynes, carbonyl compounds, esters, and carboxylic acids, and so on. Then today we shall discuss amines and also the nitriles, and then the nitro compounds and halogen compounds. And finally, we will discuss what should be our approach by looking at a mass spectrum of a compound, how we should solve the molecular structure. So there is an approach to solve that. That approach I shall discuss at the end of all these fragmentation patterns of these compounds. Okay, so today I will begin with today I begin with the amines. And amines, as soon as you see the amines, if it is amine, then you can immediately look for the molecular ion peak, whether it is odd or even. Suppose if you are sure about you don't have, suppose if you are sure that your compound is having one nitrogen, definitely that compound should give you molecular ion peak at odd molecular mass, right? Suppose if it doesn't have, or if it is having the even number of nitrogens, then in that case the molecular ion peak can be either the even number. So this is something that one should look for. So as soon as you are looking at the mass spectrum of amine, so this is a immediately you should apply the nitrogen rule and then see that whether the molecular ion peak is a odd or even. So by that you can tell that nitrogen is present or not. Okay, that is one thing. And for aliphatic amines, usually, as I claimed for many of the other categories which we discussed in last class, it doesn't give very much appreciable molecular ion peak. But if it is a longer one and is almost undetectable, okay, and then suppose if it is a aromatic amine, then there is a fair chance that the molecular ion peak can be observed. So this is a kind of common statement I have been telling to you for many of the other compounds. Okay, so keep this thing in mind. Then alpha cleavage reactions are the most important fragmentation for the amines. Alpha cleavage. So alpha means so where is the amine? So that alpha cleavage, alpha. This is the alpha carbon, and then this cleavage is most favored cleavage, and then the R can be eliminated as a radical, leaving this type of fragmented ion. Okay, so cation, and this cation, suppose if R is uh, alkyl group, very lengthy alkyl group, then definitely its molecular ion cannot be detected. But there is a signature peak that we can always get when you are dealing with the amines, that is CH2 NH2 plus peak. Okay, so after the cleavage of the alkyl radical, you will be end up with the CH2 NH2, which consists of which will have the molecular fragmented ion weight will be 30. Right, so this at 30 m by z value, we will see very nice intense, a very nice peak. Okay, so that is that is an indication for primary aliphatic amines. Okay, it's in fact it is called as a diagnostic peak. This is somewhat similar to the concept which I have explained in the case of alcohols. Alcohols give you a peak at 31. That 31 is due to what? It is CH2 OH plus. So that is the peak. 17 plus 14. So it is a 31 peak. Okay, so please remember that these are the diagnostic peaks for a certain class of organic compounds. Okay, and unlike the other compounds, other compounds, I mean the compounds having a heteroatom, these molecules normally do not give the McLafferty rearranged product. Okay, even if you have a very lengthy alkyl chain on the it's in carbon, then normally we don't see McLaughlin rearranging product in the case of amines. Okay, and loss of ammonia is not typically observed. So since it is a NH2, so we will have an assumption that it may liberate, ammonia, like volumetry or gravimetry when you are trying to do the testing, qualitative analysis when you are doing the testing. Usually when you heat it, I mean, they reduce the ammonia, right? So many other tests are there, microanalysis, semi-microanalysis. So, but unlike those experiments, that here it doesn't give any ammonia, loss of ammonia. That means that M minus 17 peak we cannot observe. Okay, please remember that the ammonia molecular weight will be 17. Okay, and similar to alcohols, it will give M minus 1 peak. That is very interesting thing. Like alcohols, it will give M minus 1 peak. Okay. And then mass spectra of cyclic amines is complex and varies with ring size. Okay, and aromatic amines will have usually will have an intense M plus ion peak. Okay, and loss of hydrogen atom followed by the expulsion of HCl. That means the 14 plus 13 is 27. So loss of 27 peak is very common. 14 nitrogen, 12 hydrogen, and 12 carbon, and then 1 hydrogen. So it is a 13 plus 14 together, it is 27. So loss of M minus 1 peak is very common in the case of aromatic amines. Okay, the mechanism is shown here, and initially it will cleave a hydrogen radical from, this is aniline, I think we all know very well, and this aniline actually will eliminate one hydrogen radical, and then it form C6H5 and H plus. Okay, this is the one that it will form later on. It will basically expel the one HCl that corresponds to 27 weight, and then we will get this one. But this one actually will immediately undergo this type of cleavage. That means that these there are two hydrogens are there here, that one of the hydrogen will actually leave as a radical, leaving that C6H5 H6 sorry C6 C5 H5 plus, right? I think so. Yeah, this is 4 carbon free alpha. C5H5 plus H5 plus 65. So correspond to 65. We can see one peak. Therefore, it's very interesting to note that, and then immediately to catch the point of with regard to the primary amines, especially the aromatic amines. Aromatic amine, immediately it will lose one hydrogen radical. Therefore, M minus 1 peak is very diagnostic. That is point number one. Point number two is that it will expel one of the the HCN from the fragmented ion, right? So HCN means that M minus 27 peak is very common. So if it is eliminating that HCN, then the remaining thing will be basically C6 H6 plus, which correspond to 66 molecular weight, the fragmented ion weight. This actually will undergo immediately eliminate the one hydrogen radical. This will form C6H5 plus. So these are the very interesting diagnostic peaks with regard to the aromatic amines. Pyridines have similar stability. That means they will have the similar stability like the aromatic compounds. And then, like aromatic compound, they do basically eliminate the expel the HCN that corresponds to 27 molecular weight, right? And this is an example of pentylamine. It's a primary amine, right? So as you can see here, the molecular ion peak is basically can be detected, but then its intensity is weak. Okay, and so once we have that, the alpha cleavage is favored, and then this will basically eliminate as a radical, and then leaving that 30 CH2 NH2 plus will be left over. So that peak we can detect in the mass spectrum. Okay, and then this is a M minus. Yeah, there is a peak at 30. You can see here the 30 is actually because of the CH2 and H2 plus. Okay, so that's the point. Then next one is the dipropyl amine. Okay, and this also, its a molecular weight is molecular end peak is basically 101. Okay, I hope that you are noticing. In this case, the MZ value is an odd number. It is 87, right? 87 is an odd number. Again, you come here and see that its molecular weight is also an odd number, 101. Okay, so one hydrogen, therefore, naturally, its M by Z value or molecular weight is going to be odd number. Then later on, the alpha cleavages. Okay, what are the two possibilities? This is one type of cleavage. This is one type of cleavage. Of course, both gives you the same product. Okay, once it cleaves here, the remaining thing can be seen over there. Okay, so this is a this is for the secondary amines, and tertiary amines that they do undergo this type of the alpha cleavage, and then leaving this as a cation and the other one as a radical. Okay, and this is a McLafferty rearranged product. So not McLafferty, basically, if it is cleaving here, the remaining thing can be basically alpha hydrogen. Actually, in the case of secondary amine, the alpha hydrogen actually will come and join here. Therefore, you can see the CH2 double bond NH plus. Okay, yeah, this is for the tertiary amine. Okay, as you can notice that its molecular weight is odd number 143, and then there is a peak at what is this number? It is 105, 110, 114. There is a number that 114 actually correspond to, once it cleaves here, that ethyl radical is eliminated, and that difference can be seen. Okay, over there. Okay, so this will undergo further fragmentation. So you can take the difference between this, and then you can note down this and try to explain. So it's a fairly easy job that anybody can do it. Okay, so next one is the amide. So in the case of amide, we do have the nitrogen. Therefore, its molecular or embedded ion, we will see at the odd value, right? Because we have one nitrogen in the case of amide. And then alpha cleavage is the most favored one. And then leaving that the fragment, NH2 CH, NH2 CO, that is the fragmented ion. Okay, that cation can be easily detected, which is very highly stable. In fact, many of the amide compound, that is going to be the base peak. Okay, CONH2. CONH2 is basically 42 M by Z value. That is a very diagnostic peak for the amides. So that is one thing. So McLafferty rearranged product is another thing. Okay, McLafferty rearranged product is another thing that we can write down the rearrangement in this fashion for an amide, and then we can always obtain this type of fragmented ion, and then leaving the compound one ethylene species. Okay, and then aromatic amides give you M-16 peak due to the loss of NH2. Aromatic amides. So usually the amide NH2, so that NH2 will be liberated from the aromatic amides. Okay, please remember that this is consistent with the rule, one of the rules that we have discussed in the case of that we discussed at the beginning. One of the rule was that alpha cleavage next to the heteroatom is the most favored cleavage. So in that respect, that the cleavage of amide from this position is highly admissible, this type of cleavage. When this is happening, then naturally M-16 can be observed. Why? Because the NH2 is eliminating with the radical. Therefore, the remaining thing can be seen as a cation. Right? A separate cleavage also gives rise to modest peak at 144. Anyway, that we have discussed. 44 is due to the CONH2 group. Okay, so this is a butyramide mass spectrum, and it is supposed to show molecular ion peak at the odd number. So it is, you can see here, it is at the odd number. Then there are peaks, so those peaks differences you can note down. Okay, and accordingly we have so many things. So this peak is for the 44. So 44 is the for the CuNH2. And since its alkyl chain is somewhat lengthy, then one can always write down this type of McLaughlin and the product. And in fact, this is going to be our uh, this is going to be our the uh, the base peak. Okay, so the base peak is at 59. One can observe the molecular ion, sorry, very intense ion. And this is the example for the amide, benzamide, and the benzamide cleavage can be obviously, the alpha cleavage, either NH2 can leave, so M-16 and M-44 are the very common fragments. As you can notice here that M, the molecular ion is actually at the 121, and this, if it cleaves one NH2 group, then it will be at 105. So this is a acetyl ion, acylinum ion. So acylinum ion 105 is very common, uh, not only with regard to the amide, but also with regard to the ketones and also the aldehydes. Remember that. Okay, the other cleavage is that the CuNH2 can be eliminated as a radical, leaving the other thing as a benzene radical, benzene cation. Okay, so that peak one can notice here. Okay, so there is one peak at 51. So what could be that one? What could be the peak at 51? You can see here that very intense stuff. This is a 50. At 50, there is one peak, and then there is another peak at 51. So what could be that 51? Can I have an answer? What could be that 51? So what could be the compound that corresponds to 51? No answer.
CONH2.
Huh?
CONH2.
CuNH2 44. CuNH2 is 44, right? It is C12, 12 plus 16, 28, 28 plus 16 again. How much it is? It is 44. So 44 is this actually. 77 plus 44. This is 121. And this is 105. This is 77 plus 28. Okay, think over and find out what could be the fragment that correspond to a peak at 51. The next type of compounds are nitrile. Again, that we can apply nitrogen rule and then say whether you can apply always that if you are know about the compound, you can always cross-check whether the molecular ion peak is odd or even. So accordingly, you can rule out the possibility of or the presence or the absence of the nitrogen. Okay, and then like many of the other compounds that we will get the weak molecular ion peak. For aromatic ions, we can see very intense molecular ion peak. The main degradation process in the case of nitrile is that M-1 peak from the cleavage of the alpha carbon. So it doesn't have nitrile CN, so it doesn't have any hydrogen. So therefore, it will not lose anything as such. But then from the alpha carbon, then there is a one hydrogen can be eliminated. So that is the most favored fragmentation for the nitriles. And similarly, loss of HCl, the 27, M-27 is another most favored cleavage. And then McLaughlin rearrangement is favored in the case of nitriles. But in the please remember, in the case of amines, that is not a favored one. But in the case of the nitriles, it is very, very much favored. and then rearranged product actually will give this type of peak. Okay, NH C CH2. So that peak actually correspond to MZ value at 41. Okay, so McLafferty rearrangement, the bonding electrons can be basically moved this fashion. Then it will eliminate one ethylene, then leaving this type of fragment CH2C NH. So that is the fragments that correspond to 41. Okay, so this is another signature of a nitrile compound. And the aromatic nitriles give a strong M plus ion peak, which is strong. And loss of HN is very common. Okay, in the case of amine or amines, aromatic amines. Okay, and then it will also lose CN. Okay, not only loss of HCN, but then loss of CN is also very common in the case of nitriles. Okay, unlike the other compounds like amines, it doesn't lose a CN alone, but then nitriles do. Okay, and this is an example of a propionitrile. As you can see here, its molecular ion peak is seen at 55, which is an odd number. Okay, and then at 54, there is a loss of one ion. So definitely we can conclude there is a possibility of the amine. Why? Because that it always prefers to lose one hydrogen radical. Okay, so that is one type. And then from this, actually, it can eliminate one HCN or HCN. Okay, HCN is basically 27. It is a 14 plus 13, it is 27. So M minus 27, so is very, very favored in the case of nitriles. And this is the Valero nitride. Valero means a pentanitrile, okay, pentanitrile. And as you can notice here, at 83 there is a peak, and this peak actually from this fragmented ion that there will be elimination of. Okay, there will be elimination of this type of cleavage or this type of cleavage. Alpha cleavage is a cover. So if it is cleaving at this position, then it will leave out a peak at MZ value 41. Okay, and the other type of fragmentation is this type of thing. So it is basically beta and delta carbon break is the another one. Okay, and the next type of compounds are the nitro compounds. So the same discussion in the case of nitro compounds also, that we can apply nitrogen to, and then we can judge whether there is a presence of nitrogen or not. Okay, and most of the aliphatic nitro compounds also do not give any kind of molecular ion peak. Okay, but aromatic compounds do give the molecular ion peak. So that is the difference. As in the case of nitrile, also the same thing happens. Okay, so the principal degradation in the case of nitro compounds is the nitro, NO. NO means 14 plus 16. That corresponds to 30. That corresponds to 30. So there is a kind of dilemma, whether it is a CH2NH2 or CH2NO. Right? So there is a dilemma, right? So the dilemma you have to carefully cross-check with the other rules. Okay, whether it is a NO or whether it is something else, because the 30 also can be due to what we just discussed. 30 is due to this type of one, CH2 and H2 fragment, that the primary amines. So the 30 can be primary amines, or 30 can be due to the loss of even this type of NO radical, NO plus. Okay, so that keep in mind. And then the other degradation process is the NO2 plus. Okay, that corresponds to 46. So M minus 30 and peak at 30, and also M minus 46. These are the very common peak that we can observe. And the aromatic nitro compounds. This is an example. As you can notice here, that the nitro compound, nitrobenzene, is eliminating one oxygen, leaving one nitrous oxide radical, and then we will get actually the C6H4 plus cation, which can be observed in the mass spectrum, eliminating the CO. Okay, I told you this is one of the way of fragmentation. In the case of phenols, I mentioned that phenols actually immediately they undergo elimination of hydrogen. After that, you will have a C6H5O. From the O, that there is expulsion of the CO. Right, the same thing happens even here also. That initially it will lose one NO radical, and this will be further subjected to this will undergo to the further fragmentation process and leaving that C5H4 plus carbon monoxide that fragments separately. Okay, keep this thing in mind. Okay, on the other hand, that the nitrobenzene can also eliminate simply, leaving this as a radical and keep leaving this as a cation. In that case, that this can undergo this type of C4H3 plus. That the C4H3 plus actually is correspond to 51, right? So this is another way of fragmentation. So therefore, in the case of the nitro compounds, especially in aromatic nitro compounds, we can have always a loss of 30 peak. Okay, a loss of 30 peak. That means at 93 MZ value at 93 we can find one peak. Later on from this one CO can be eliminated. Sorry. From this one CO can be eliminated and leaving the other C5H4 cation can be found. Okay, and the other way of fragmentation is that N2O can be eliminated. N2O radical can be eliminated, leaving that C5H5 plus. Okay, and then benzene cation can undergo further fragmentation process, and it can leave C4H3 plus. So this 51, what I was talking in the previous case, is actually C4H3 radical. Okay, so cation. I'm sorry, actually, I have gone for the certificate verification of some non-teaching post. There they have given a lot of alcohol. So the alcohol I smelled, still I have that smell. So I'm feeling a lot of drowsy. I'm sorry for that. Okay. So the other compound is the 1-nitropropane. 1-nitropropane, and propane, you can see here the nitro compounds, I made a point that they do not give molecular ion peak. Okay, so this is exactly precisely is the case. Okay, so the at 89 there's supposed to be a peak, but then there is nothing. Okay, that is one example. Then the NO2, that the M-46 is very common. I said that therefore 89 minus 46, so there is a peak at 43. So 43 you can see a strong peak over there. Okay, so this is the in fact this is going to be a base peak. And then NO radical and then cation. This also we can observe here. There is another 42. So what could be this 42? Any idea? Sorry, at the 41, there is, this is also very intense one. So 41 is due to what? If 41 is due to what? There is a peak at 41.
Propane group.
Propane. What is the propane? C3? H7, right? That is 43. 43 is fine, but then I'm asking 41, there is a peak. What could be at 41? To find out, I will also find out that. Okay. Then the next example is that aromatic nitro compound that the paranitro and is the very interesting fragmentation pattern. So 137, there is an intense molecular ion peak, and then the NO can be eliminated, right? In that case, that it will be left with the C6H5 O plus radical, the cation, So that corresponds to 107. At 107, there is a peak, right? And the other possibility is that it can cleave, this way. The total NO2 can be eliminated. In that case, that corresponds to 91. And then 91, whenever you have a 91 peak, that cation, okay, that can undergo to the next step fragmentation, where it can eliminate one carbon thing. Then it will form this type of C5H5 plus. So whenever you see a benzene will immediately further fragment to give C5H5. So this is very common type, or so it is already here. So benzene will directly give this type of fragmentation. Whenever you have a benzene cation, that cation actually will give loose small fragments and will give you C5H5 plus. Okay, cyclopentane cation. Okay, so this is the one way of cleavage. Okay, so what are the things? So in the case of nitro compounds, this NO and then 2O. Okay, those are the common fragmentations. And then from nitrogen, from here to this one, C5H5 plus. So C5H plus 60 plus 5, 65. So 65, 91 minus 65. How much it is? It is 6 plus 2 is 26. So what could be this one? Is there any explanation for this? What could be this elimination of 26?
Nitromethyl,
Hmm?
nitromethyl or something like that.
What account the 26? Okay, let me verify this also, this fragmentation process. So this is understood that 91 peak, the base peak, the elimination of that 46, that corresponds to the NO2, right? And also another peak, it is because of the loss of M minus NO. NO correspond to 14 plus 16 is 30, right? So 30 peak is understood. Okay, this peak and this peak are understood or understand to us, but then this particular peak C5H5 plus is actually coming from either this or this. That is my question. Okay, so this can come either from this or from this. Maybe probably because is due to maybe from this, I think so. So expulsion of CO, I think that was the, maybe that is the origin. 16 plus 12. Suppose if it is losing, cleaving one CO, then that could be one. I think perhaps that is the reason that the expulsion of a CO is perhaps is the reasoning for observing this peak. Okay, so let me work out on this also. The paranitrotoluene compound also, I will check it out. The next one is the halogen compound. So halogen compound mostly we have discussed. There is nothing much to discuss, but let me go through quickly. The halogen compounds will give usually very nice intense molecular ion peak, especially with regard to the chlorine and bromine. They give very nice intense molecular ion peaks. Okay, fluoro and iodo compound do not give any appreciable contribution to the isotope, but except the fluorine and the iodo compounds, the other isotopes can be observed, especially with regard to the chlorine and the bromine. Okay, so M plus 2 peak is very much common in the case of chloro and bromine compounds. And chlorine compound, if it is there, then easily we can understand from the intensity of molecular ion as well as the M plus 2 peak. So the ratio of the molecular ion and the M plus 2 peak will be 3:1. Okay, so 1/3 of the molecular ion peak will be the intensity of the or the height of the M plus 2 ion peak. Okay, in the case of chlorinated compounds. Suppose if it is a brominated compound, almost equal intensity, peaks correspond to M plus molecular ion as well as the M plus 2 we can observe. Suppose sometimes we can also see M plus 4 and then M plus 6. In that case, that you have to immediately conclude that it is not that only one type of isotope, one type of halogen, but then there is a combination of halogens. Only then that is possible, that M plus 4 and all. And not only that, sometimes if you have more number of chlorines, or sometimes you have more number of halogens, other halogens, it will happen. If it is only one, then we can only observe the M plus 2 field. Okay, so if you have a 2 chlorines, then M plus 4 peak is possible. Okay, if you have a 2 chlorine, the 2 chlorine can actually exist in the M plus 2 state, then for that can contribute to the M plus 4 peak. Okay, if you have 3, M plus 6. Okay, if you have 4 halogen atoms, especially I'm only talking about the chlorine and bromine, then actually they can give to M plus 8 also. Clathrate compounds, okay, fluorinated compounds like CF3, okay. So those type of compounds, they give the NMR spectrum where the molecular ion peak actually is associated with M plus 2, M plus 4, and then M plus 6, whose intensities are actually governed by the number of halogen atoms which are present, especially the chlorine and bromine compounds. Keep that in mind. And the fragmentation mode is that immediately it will lose one halogen. Halogen will always prefer to leave as a radical in the case of halogenated compounds, leaving the other alkyl thing as a cation. So the cation, the alkyl cation can be easily observed. Okay, so M minus halogen, if it is a chlorine, it is 35. So that is very, very common. Okay, halogen will prefer to leave as a radical. Please remember that. Okay, and the leaving group ability contributes to the loss of hydrogen strongly for iodo, bromine, less so for the chloro and then the fluoro compounds. Of course, that we can easily understood this concept. And the loss of HX is the second most common mode of fragmentation. Loss of the HX, okay, hydrogen halide. So this is another type of this one, okay. And therefore that M minus X peak and M minus X peak. So both are the, M minus HX and M minus hex molecular ion peaks are basically very common in the case of halogenated compounds. And alpha cleavage is the another way of cleaving, especially when there is alpha cleavage, then it will leave the radical, alkyl radical will be left over, and the remaining thing, that CH2 X plus can be observed, just similar to that of the amines or maybe the nitriles that we have seen. Okay, the other group is eliminating as a alpha cleavage, actually leading to the elimination of the radical, leaving the other one as a cation, fragmented cation. That cation can be observed. CH2 double bond X plus is very common. And the longer alkyl chain, okay, longer alkyl chain. I mean, if you have a very lengthy alkyl chain, okay, and the carbons which are above the delta carbons will normally eliminate. The carbons which are above the delta carbons are normally eliminated. What I mean is that, okay, so this is a halogenated compound. So this is alpha, and this is beta, this is gamma, and this is delta. So this is delta position. So now what I'm saying, what I'm claiming that, okay, above the delta carbon, this is the delta carbon. So above the delta carbon, whatever you have, that will, here in this case it is R, this R will be eliminated as a radical. That is the point I'm saying. Okay, so this is another important fragmentation with regard to the halogenated compounds. Aromatic halides give you strong molecular ion and typically lose the hydrogen radical atom from the C6H5 plus. So that is understood. That this is aliphatic aliphatic halogenated compound, that is 1-chloropropane. As you can notice here that we don't see very very intense molecular ion peak. But still, you can always make out the difference between these two intensities. Molecular ion at 78 and then at 80 there is a small peak. Of course, these are not very prominent, but then still you can make out the point what I'm talking about. M plus molecular ion is at 78, M plus 2 at 80. You can see there is a 1:3. Okay, where 3 is the molecular M plus ion and then 1 is the M plus 2. Okay, so that is what I'm saying. And then, as I told you, that the alpha, halogen prefer to cleave as the radical. That is one way, and leaving the other alkyl thing as a cation. In fact, that is the base peak. Okay, the other one is the alpha cleavage here, alpha cleavage. So the alpha cleavage is here. This cleavage leave the fragment like CH2Cl, CH2Cl. So those peaks are also can be Cl. So 35 plus 14. That is the one that you have to remember. And another example is the aromatic compound, aromatic halogenated compound, that is a parachlorotoluene. And the parachlorotoluene, as I told you, that the chlorine can be eliminated, leaving that. Yeah, here that is very, very common. First, I think let us look at the interesting thing, what I was talking about. This is of this much height, whereas the M plus 2 ion peak is this much. So there is a nice correlation between the molecular ion peak at 126 and then at 128 there is a peak. So if you consider this as a 1 unit, this is going to be 3. So 1:3 ratio that we can see. So here nicely is visible. The next thing is that the fragmentation when it comes to the halogenated compound, then the alpha the halogen can be eliminated as a radical, that leaving this compound as a 91. So 91 will subsequently will undergo this type of fragment C5H4 plus is another one, so that you can find corresponding peaks over there. Okay, and this is an example for bromo, 1-bromobutane. And as you can see here, that is the point I'm talking about in the general discussion. So there is a peak at 136, and there is another peak at 138. So both are of the same intensity. So this means is that whenever you come across this type of equal intensity peaks in the extreme right hand side, that gives you immediate conclusion that you can make out that there is a possibility of bromine. And not only that, and sometimes that will also carry forward to the even fragmented ion also. Here there is something happened. Even that also you can see there are two peaks with the same equal intensity ratio. Okay, the suppose if you take the alternative, it's not an alternative, it's a conjugated MZ values that one after the other. So you can see here that the intensities are almost same. So this also gives, if you are working with organic chemistry compounds, NMR and the mass spectrum, that we come across this type of thing in our compounds in my lab actually. It's not only here, but then inside the fragmented species also we used to see peaks per corresponding. Especially when I was working with the NBS reaction, the bromination, sorry, NBR reaction, N-bromosuccinimide is one brominating agent. Of course, we have very strong brominating agent, bromine, we can do it, but then bromine is not selective, but the N-bromosuccinimide is a very selective brominating agent, so it will precisely go and then sit at one particular position. So that bromination and further reaction on the bromine atom we used to do. So bromination is the first step. Later on, we used to do some kind of CC bond formation reaction. At that time, when we submit this brominated compound, we get not only the fragmented ion, the molecular ion region, but also the fragmented ion. This region also, we can see nice peaks like this. Okay, almost equal intensity we used to say. So that confirms the presence of the bromine atom. Okay. And of course, you can apply all these rules. Alpha cleavage can be applied, and accordingly, you can get the base peak here, right? And in this case, this is alpha, this is beta, this is gamma. So, and then this is delta. So there are, of course, you can write down McLaughlin rearrangement type of thing, right? And then corresponding peaks can be observed in the mass spectrum. And this is a bromo compound, parabromotoluene. As you can see here, here also 170 and then 172. Both are of the same intensity. You can notice two peaks. That shows clearly that there is a presence of bromine. And then again 91. Whenever you see a 91, then definitely it is supposed to be this type of toluene type of cation, right? Benzyl cation, of course. We should not say toluene cation, it is a benzyl type of cation. And then 3,4 dibromotoluene. 3,4 dibromotoluene. So here there are two bromine atoms. If there are two bromine atoms, then you can notice here not only the M plus 2 peak, you can also notice M plus 4 peak. Can you notice here? So at 248, there is a peak, that is the molecular ion, then 250, and then 252. So this is actually M plus 2, and this is M plus 4. So there are three peaks up there. So when you have more than one halogen atoms, then we will come across this type of isotopic peaks. Okay, but you can always notice that here you don't see, because you may think that this only happens, equal intensity or 1:1 intensities. You can only notice when there is only one halogen. But if you have more than one, then their abundance actually govern the M plus 2 and the M plus ion, and also M plus 2. Therefore, you don't see that actual thing 1:1 or 1:3 ratio. So we'll see something different. But in that case, that we can notice that these peaks. Suppose if this cleavage happening, you can always have one bromine atom on the benzene that will give the almost equal intensity for 169, 171. Okay, so what are those things? Those are the fragmented ions. This is the fragmented ion if it is eliminating one bromine. Okay, so 169, you will see that. And along with the 169, we will also see another peak at 171 with equal intensity, primarily because of the M plus 2 ion peak. Okay, and then of course, if this cleaves, of course, when you have a multiple halogen atoms, so all the halogen atom can eliminate one by one with the radicals, so leaving the other one as a radical. So at 90, we can observe this type of molecular ion, right? And then IDO compound. As I told you, that IDO compounds usually do not show any isotopic peaks, very intense isotopic peaks. Instead, they give the M plus 1 peak. M plus 1 peak, that we can easily make out. Okay, M plus 1 peak we can easily make out. But the iodo compound do not, the M plus 2 isotopes, that is not having very much abundance. Therefore, it will not show M plus 2. But M plus 1 peak mainly comes from the 6 carbon atoms. Okay, and then like the other halogen atom, so it can cleave at this position, leaving that iodide. Okay, iodide radical it will eliminate, then leaving that benzene cation. Okay, so with this, I think more or less we have finished the discussion of the halogen compounds, and also the most of the general compounds, most of the organic categories that we have discussed. So next class onwards, we shall discuss a couple of problems. Okay, maybe one or two classes I shall discuss the problems, so that you will appreciate you will appreciate the general principle what we have learned so far. Okay, so this is the foundation, right? Unless you have this foundation, you cannot work the problems. So I have now laid the foundation for understanding And what is the mass spectrum? I started with the basic theory, and then instrumentation part, okay, and then what type of molecular, what type of ionization is possible, and then what type of analyzers are there, what type of detectors are there, and there onwards I have entered into the discussion of the fragmentation principles, and we have discussed all these things. Now, hereafter, maybe in one class or two class, I am going to discuss about few problems. Okay, for all these problems are possible only if you have studied and then come to the discussion. And if you don't study, and it is going to be really a boring job. I will be asking question, and if you are not answering, then you will not be able to get the uh, full essence of the subject. Okay, you should read all these patterns and then come. Okay, in the next class, I suggest all of you to come like that. So it is like a NMR discussion, the chemical shift values. Unless you understand you remember and memorize the chemical shift values, we cannot interpret the NMR spectrum. Likewise, here, unless you understand the principles, fragmentation principles, it is not possible to work out with the unknown problems. So we read those things and then come in the next class. But before that, before I conclude my lecture for today, I shall discuss what is our approach. What should be our approach? When we are solving when we are solving the molecular structure puzzle, okay, in the examinations, okay. This, what we should do when you first you look at the spectrum, okay, and then just give a small look, okay, how complex it is or how simple it is. And look at, you just open your eyes and look at very carefully, and then later on you start extracting information from the peaks. Okay, how to extract the information? There is no way. You have to study the fragmentation principle, and then only it is possible. If you are blank, in the other point, the fragmentation rules and all those things, then definitely you cannot answer. But if you are there, then definitely immediately you can make out certain conclusions, and those conclusions you please note down one by one. Okay. The first and foremost thing is that you just try to the first point is that where is your molecular ion peak, that you should try to identify in the given mass spectrum. Okay, in the given mass spectrum, where is your molecular ion peak, which direction it is. Okay, then try to see that whether it is a weak or strong. Okay, that is a general conclusion. If it is weak, then it can be, there is a possibility, most of the cases it is going to be it is going to be a aliphatic one. If it is strong, there is a chance that is going to be the aromatic compound. So that is one thing. The next thing is that around the molecular ion peak, are there any isotopic peaks? My molecular ion, is it having only the m plus 1 peak, or whether it is having m plus 2 peak, or whether it is having m plus 4 peak, or m plus 6, and so on. Okay, so that is also that immediately you have to identify. Identification of the molecular ion is the first step. Second step is that isotopes. What are the isotopic peaks that I have, and what is the nature of those isotopic peaks? Okay, when you see m plus 2, then look at the intensity ratios and make some conclusion. Okay, if there is a 1:3 ratio, then okay, write down there is a possibility of chlorine. Okay, there is a 1:1, there is a possibility of bromine. So these are the conclusion that one has to write. M plus 1, when you see the m plus 1, okay, and I told you that roughly how to estimate the number of carbon atoms in the given molecular structure. If it is 7%, so roughly, then there will be approximately 6 to 7 carbon atoms can be there. If it is 7 to 8, the intensity of the m plus 1 peak, then there is a possibility of 6 to 7 carbons. Okay, so that kind of conclusions one has to draw after looking at the isotopic peaks. And similarly, you also apply nitrogen rule to the molecular ion peak. Having understood having identified the molecular ion peak, the next step is that you try to apply the nitrogen rule, whether it is odd or even. Okay, you write down something about it. Then you can also apply the nitrogen 13 rule of 13 rule, and then see whether you will be able to draw something out of that discussion. Okay, what is the rule of 13? Then, divide the fragmented ion peak or molecular ion peak, divide with the 13, and then the remainder will give you something n plus r. Okay, so that is another thing that you can do. From there, you can make out something. Then apply the HDI, hydrogen deficiency index. You try to apply that. And similarly, you also look at is there any M minus 1 peak? Because M minus 1 peak is a signature of couple of categories of organic compound. The best example is what? Halogens and then alcohols, right? So these are some of the things. Okay, you can or acetyl, alkynes, terminal alkynes also will cleave on hydrogen radical, right? So, and then amines, right? So those things you write down. If you see a minus 1 peak, then what could be those? So you write down those things. Okay, and the other one is look at the base peak. The next step is look at the base peak. Base peak is the one which is having the highest intensity or the max 100% intensity. Relative abundance should be 100%. So you try to locate the base peak in the mass spectrum and then see that. Sometimes the molecular ion peak itself, it will be 100%. So that is also a base peak. So you may not have a separate base peak. So that also keep in mind. Okay. And if it is, try to locate the base peak, and then you try to assign something to the base peak, because the base peaks are actually are the ones which are very stable, and then are staying for a relatively spending relatively a longer time in the mass spectrum. So those can be due to some kind of common factors. For example, some of the cases like CONH2 is going to be your base peak, or McLafferty rearranging product is going to be your base peak. Okay, some of the common peaks that we can see, or retrodeal solver product is going to be your base peak, right? So those things, after looking at the base peak, you just try to interpret that MZ value to whether it could be that, or whether it could be this, or whether it could be that. So you try to get some information out of that. Okay, you write down whatever you get the feeling, you just write down whatever you got the clue out of the base peak, you just write down that. Of course, to get the clue, you have to study the fragmentation rule that we have discussed. So if you don't study and then try to work out, then definitely it's going to waste of time, and that will affect the answering the other questions also in the examination. So please keep in mind. There are people, they think that it can be easily done at last. No. When you have peace of mind, immediately you can work out. But at the last minute, if you are trying to work out NMR problems or spectroscopy problem, you are going to be in really soup. Okay, keep that. And then later on, after having the fourth step, or within the fourth step, you have to do another thing, like what are the fragments. You just take some intensity as a reference, and then above that you look at, okay, if you have seen some intense peaks above 20% relative abundancy, you will try to look at those things. What could be this peak? Are there any fragment lost from the molecular ion or the fragmented ion? If it is lost, what could be that? To do this, what you have to do, you have to take the difference. You have to take the difference between the molecular ion peak or the fragmented ion peak. So you try to just do this simple subtraction from M by Z value, a peak at one particular M by Z value with the other position. That way you will be able to identify or assign some of the fragmented peak, right? The best example is that, okay, some of the compounds I told you, okay, if you have a nitro compounds, then initially they will lose NO. Another way of fragmentation is that NO2, right? So those things, from suppose it is the case like NO2 at once it left, or initially the NO was cleaved and then later on the oxygen, so that it will be reflected in the mass spectrum. when you look at the subtraction, when you do the subtraction from one peak to the other peak. Okay, so having identified the base peak, and later on look at the somewhat intense molecular ion peak, the fragmented ion peaks, and try to assign some fragment to that. Okay, some fragments means, of course, there should be a reason for that. Okay, you just take the difference between the molecular ion peak and to that particular Benson value peak, and then try to assign that number to something. For example, when you take the reference is 14, okay, and if you see a 14 difference between the some reasonably good intensity the fragmented ions, then that could be alkane. If there is a 14 difference, that could be alkane. So there is no other way, right? Like that, you have to apply. Okay, identification, and also next you try to work out with the unknown ion species. Okay, and then look for some loss of some of the common neutral species from the molecular ion. Okay, this is what I was telling. Of course, this is the extension of the previous point which I discussed just now. Of course, are there any neutral species like CH2, CH2, or acetylene, or water, or ROH, or HCl, HC, HCO, or CO, or HS? So, are there any species neutral or little bit of known fragments are left or cleaved from the molecular ion? Okay, if yes, what could be? Okay, so this can be, again, you can do only when you take the differences and you subtract the position of a particular ion with respect from the molecular ion position and there's a value, then that difference will tell you. Okay, if there is a loss of 28, the 28 can be your ethylene, right? CH2, CH2, right? Similarly, the CH, if there is a loss of 18, that can be a water, right? If there is 27, that can be your this thing. Okay, 28, HCO, okay? So that kind of, or aldehyde is there sometimes. Aldehyde also can be eliminated. Of course, it doesn't come on a neutral, but then the group, certain known groups can be eliminated. So in that it will come, and CO can come. Okay, so, and then hydrogen halide, the HX also can be one of the neutral species that we can think of based on the value. Okay. And later on, you also look for some of the diagnostic peaks in the spectrum. For example, 29, 30, 31, 45, 59, 77, 191, 105. These are all something that we discussed. 29. 29. What could be 29? Can anybody? Is aldehyde, right? 29 can be aldehyde. CHO 12 plus hydrogen 1, 13, 13 plus 16. So 29. So that is the one. 30. So 30 is CH2, NH2. Or 30 is CH2, some other thing that I think NH, CN, I think so. So we have assigned. And 31 is alcohol, CH2OH. And 45 is something else, I forgot. Okay. And then 77 is the benzene carbocation. Okay. And 91 is the benzyl one. And 105 is the acylium ion, that C6H5CO, that type of ion. So when you look at some of the position of the peaks, if you find the peaks at these numbers, that means they are belongs to so and so category. Okay, so that information also you write down, and then having all this information, now you have a piece of information, another piece of information, another piece of information, another piece of information, and all these pieces of information you try to stitch together such that you will get a molecular structure. Okay, so this is where most of the students actually make a mistake. Okay, when you are given a piece of cloth, many cloths, and if you are asked to stitch it, there are many ways to stitch it, right? But only one option is there, That is what, but answer is only one. The molecular structure data is for one compound. So your answer has to be exactly that one. Only then you will be given 100% marks. So when you are stitching, you should not stitch such that it doesn't fit the data. Okay, you can stitch anyway. Okay, when you are working with, initially you will stitch in one fashion that that molecular structure may not suitable to the data which is applied to you. So after stitching, you have to basically again you go back to the data and then cross check it. Okay, this data is collected based on few things, and later on, after having some kind of rough idea, then whether that rough molecular structure explain all the peaks present in the molecular spectrum or not, that is something that is a cross checking. The final cross checking is something that most of us, the student doesn't do it. Okay, if you don't do that, if you are getting good structure, then is nothing to worry. But most of the cases, 95% of the students, they make mistake here. You have to cross check the data. Simply when you see 30, the 30 can be not one, it can be few other things as well. Oh, you only studied only 30 is correspond to so and so. If you but then 30 correspond to something else also. If you forget that, and if you only remember this, if you answer, okay, that is where you will go wrong, and that your entire answer will be wrong. Okay, so that cross checking thing one has to do thoroughly before assigning. After assigning the rough structure, you just try to go back and see whether all the intense peaks are satisfying. First check. Later on, whether all the somewhat moderate to intense peaks can also be explained with this type of molecular connections or the functional group connections. That is something that you have to cross check and accordingly propose the structure. Okay, when you are answering, then in the examination point of view also, especially the end semester examination, you have to write down all these things, because these are all, if you do this systematically and do this, even if you don't get the exact structure for which the data is given, since you have identified a couple of ion peaks or the molecular ion peaks or fragmented peaks, then we will give you some marks. Okay, when you are working with the descriptive answers, you have to give the reasoning. Okay, this is due to this. This can be due to this. This can be due to this. So then, after writing all these things, at the end you propose a structure, and that structure is correct or not, you judge it yourself, and then try to explain all the peaks. And if it is okay, you leave it as such. If it is not so, then you rework out so that it will match with the expected molecular structure. Okay, and many students simply will write some structure. That some structure will not be helpful. Just writing the structure will not be helpful, especially when you are working with the lengthy answer, long answer questions. You have to work out systematically so that that will be appreciated. Accordingly, marks can be allotted to you. Okay, so with this, I have completed for today, and if you have any questions, maybe I shall take.